Hello, in this video we're going to derive some generating functions for a Poisson distribution. Here's the density for a Poisson distribution, and we're going to find the factorial moment generating function, the moment generating function, the characteristic function, the probability generating function, and let's just jump right in. So the factorial moment generating function is e expected value, or it's eta of t, which is expected value of t to the x. So plug in t and then multiply it times the density. Well, the exponent is x, so we can combine that into this, but then that's the new lambda, so we need an e to the minus, with that same lambda, but if we add that, we have to subtract it, and so it doesn't change this density, and this is a constant, so we can factor it out. But this is a new Poisson distribution, which sums to 1. So we're left with just this, and you combine the exponents to that, and that's it. That's the factorial moment generating function. So let's use it once. So the first factorial moment is the derivative of eta evaluated at t equals 1. So if we take the derivative of this, we get this function here evaluated at 1. This drops out, and we're left with lambda, which we know is the mean of a Poisson. So the second factorial moment, and it's called second because there's 1, 2 terms, sometimes called a falling factorial. You take the second derivative of eta, or the derivative of this, and you get this function here. It's evaluated at t equals 1, and you get lambda squared. So to calculate the variance, this is a formula. So really this piece right here is the expected value of x squared, and then minus the mean squared. This we just calculated at lambda squared. This was lambda, that's minus lambda squared. Those drop out, and we're left with lambda. And that is the variance of a Poisson distribution. So let's look at the moment generating function, m of t, which is defined to be the expected value of e to the tx. So you plug this in, take it times the Poisson. Now this exponent here we can combine to here, and now what we want to do is kind of trick this into looking like another Poisson distribution. So we get rid of that, but we need an e to this lambda. So if we add it, we have to subtract it. So that's what we do here. So we add this, but then subtract it, and that should be a minus in there because we want minus lambda. And so if this is our new lambda, then we want minus that there, and then we add it there, so it drops out. Now this sums to 1, which leaves this, and then that is the moment generating function for a Poisson distribution. Characteristic function then becomes easy after you find the moment generating function. So phi of t is the expected value of e to the itx, which is the moment generating function evaluated at it. So you plug in it wherever there's a t, which was here, and that is the characteristic function. So now we can find the moments from that too, taking derivatives and evaluating at 0. Now the probability generating function is actually, we've already derived it, and that's the factorial moment generating function. But instead of evaluating it at 1, we evaluated it at 0 and divide by this factorial here. So if we want to find the probability that x is equal to k, we take the kth derivative of it, evaluate at t equals 0, and divide by k factorial. So as a quick example, if we want to find the probability that x is equal to 2 in this Poisson distribution, we take the second derivative of eta, which we already did on the previous page, which was this, and of course we have to divide by 2 factorial, evaluate at t equals 0. So here that's 0, then the minus 1 is left, and we get e to the minus lambda, that and lay them to the t, and we have 2 factorial. And that's the probability that x equals 2 in a Poisson distribution. Well, that's all I have for today. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.